right, so this is the second half of 8.4. We're just talking being introduced to this rational exponent idea. So we had something like 8 to the 2/3 is 8 to the 1/3 squared, right? And we could change the 1/3 part to a cube, and then we square it. We can simplify it down to 4. And it was shown, multiple times that you could go either way. It's totally up to you. This next situation is gonna, so this is just a little more on that. We're going to work with these a little bit more, get some more examples, and then we're going to start simplifying things, okay? See if we can simplify some of the more complex ones with some refresher ideas. So first off, basic of the basic, 13 to the 1/2 power, what does that equal? Square root of 13. All right, so that's just definition of a rational exponent, okay? 6 to the 3/4, two options here. I could do the 4th root of 6 cubed, or I could do 6 cubed and then 4th root it. I think I'm going to go with the hard part first. Let's do the 4th root of 6 cubed. Well, the 4th root of 6 is not a whole number, and so I don't think I want to simplify that expression. I could do the 4th root of 6 cubed, in which case the 4th root of 216 might look a little better. Okay. Either way, I'm not going to get a whole number, because if they're equal, I shouldn't get a different answer going a different way. But I think this one might be a little prettier. Okay. Next one, again, I might go with the root first, in which case I do kind of get a little stuck, because I don't know m, and so I can't actually take the 8th root of m. If I went the other way, and I want to put parentheses around that if I went the other way, or give them both a 5. Either way is fine. But either way, I don't have enough to take out a group of 8. And so really at the end of the day, these two are probably equivalent. Over here, we see an extended example. This does apply to addition and subtraction as well. It's one of the few things that it doesn't change what we do. And so we have the square root of 3x plus 4, either cubed on the outside or cubed on the inside. Just remember that you cannot distribute that 3, in which case either one of these would be our answer. It does work the same way with variables as you've seen. We could just take this variable here. We've got a negative in play now. Let's see what happens when we start with that negative. If I do 1 over r to the 2/3, so I've used the negative first, and then I can do the cubed root of r squared. Well, that doesn't give me anything that I could simplify. 3 cubed root of r squared, again, I don't see anything I could simplify. And so I'm kind of stuck at either one of these. All right, the last one here, the square root of a squared plus b squared. You may recognize that mini phrase there, a squared plus b squared. We know it to equal c squared. This, in fact, equals c. If you can see that. If I had squared on the other side, I would square it over here. It definitely does not mean that a plus b equals c, because I am not allowed to simply cancel those squareds and the square roots due to that plus sign there. So just keep that in mind. That's just a little reminder of everything from the last video. Okay, let's go backwards now. Let's see if we can write the rational exponent from the rational expression. So let's write this exponent here. Well, the base would still be 10, right? But what power is on it now? There's a 2 here in the index, so 1/2 would be the power. Over here we have 3 to the 1/4. We have 3 to the 8th being raised to the 1/4. I could simplify that a little bit by multiplying 8 and 1/4 to get 8/4, which reduces down to 2, which reduces down to 9. So that's something that could be a little convenient, right? We can simplify that way a little bit. But that is what it would look like in exponent form. Over here, what would this look like? Z to the 6th power, the 1/6 power to the 5th, or z to the 5/6. Over here, I got to be careful. I have x to the 1/3 times x to the 1/2, which means I have x to the 1/3 plus 1/2. So that's just a flashback to one of our exponent rules, which we are going to revisit in just a moment. If you have two bases that are the same, you can multiply them. If I have two radicals that are different, I can't do anything. If I change them now to rational exponent form, I have a lot more wiggle room. I have two of the same base. There was a problem earlier in 8.2, I believe, 8.3, somewhere around there, where we had two bases that were the same. We had two twos, but we couldn't do anything because one was a fourth power, one was a fifth power. If we were to change those to exponents, we now could do something about it. And so let's finish this one out. X to the, let's see, if we made both of them sixes, this one would be 2, 6, that would be 3, 6, and we get x to the 5, 6. Now, if you're not sure about your fraction addition, you will want to buff up on that in this chapter especially. Okay, next up, we're going to simplify. We're going to kind of build on D here. We're going to bring back our exponent rules. Luckily, the rules are not going to change, so let's just recall them all. This first one says if you have two of the same base being multiplied, you can add their exponents. If they're being divided, you subtract their exponents. We already saw this one. If you have a negative r, it's going to turn it upside down and give each of them a positive r. If you have 2 or 1 to 2 powers, is the same as multiplying them. If they are all multiplying, you can distribute that exponent. If they are all dividing, you can distribute that exponent. And if you have a negative power, it will flip over. So those are your exponent rules. They're all written in variable format, so that saves some space for you. If that is not going to help you remember them, then I recommend you write down some notes within those exponent rules about ways you, as your own educator, can help remember, okay? But let's take a look at some examples. So here I've got 2 to the 1/2 times 2 to the 1/4. Well, if it was just 2 to the 2nd times 2 to the 4th, I would add that, it would be 2 to the 6th. Now, careful, it's not going to be 2 to the 1/6, but I can do the same thing. I can add 2, or I can have 1/2 and 1/4. And to do that, I would make them both out of 8. No, I wouldn't. I could make them both out of 4, Miss K. Least common denominator, meaning I only had to change the second one. I get 2 to the 3/4. So remember, when you're adding fractions, try to make the same denominator, in which case I just needed to change the first one by multiplying it by 2, and therefore I multiply 2 to the top as well. Add the numerators, you get 3/4. Let's do it again. We've got 5 to the 2/3 being divided by, I'm just going to rewrite this in a slightly different way. I'm going to use a division symbol instead of a fraction, because there's way too many fractions going on here, right? And so we have this nice division symbol to help us clean this up a little bit. In which case I can do the same thing, except this time I will subtract. Okay. Same denominator here. That's very convenient. So I get 5 to the negative 5/3, but I don't like the fact that it's a negative, and it does say right with only positive exponents, so I better apply that negative power rule. There we are. Now, since it doesn't explicitly say that I need to change it to a radical, there's no way that I need to do that. In case it did, though, this would be the cubed root of 5 to the 5th, and I could actually keep going. I could keep going a lot here. I could simplify out that group of 3 5s I see. I could rationalize the denominator, right? There's a lot of different things I could do. But at this point, we're just working with our exponent rules, right? If you did want to finish this out, I could easily see 5 cubed root of 5 squared, in which case I'd multiply by another root 5. So I get 25 on the bottom and cubed root of 5 on the top. So this would probably be the best answer, but this would be a perfectly acceptable answer here. All right, cool. Let's go to the next one. Let's work with some variables now. So where you'll probably see more of these. This looks like a hot mess. Straight up a hot mess. The cubed root of x squared times the 4th root of x. That's so hard to see how I would put these together. So the very first thing I want to do is rewrite these in exponent form. And I gotta be careful about this. I don't want to write that first one as 3/2, even though it's tempting. It's a cubed root, and so the cube is going to go in the denominator. Now they're multiplying, so I'm going to go ahead and add them. And I gotta be careful about my fraction addition. Both over 12. This one I had to multiply by 4. That one I had to multiply by, no I didn't, just kidding. This one I had to multiply by 3. So I get 6. And this one I had to multiply by 4. And so we get 10 over 12 as my exponents, as my x's exponents. All right, this one also kind of hard to see with all these radicals going on, so I'm going to rewrite it as x cubed over square rooted and x squared over cubed rooted. They are dividing, and so I will need to subtract those two. Okay, be very careful here. Still need sixes. Even in subtraction, you want a common denominator. So times this one by 3, you get 9. Times that one by 4, you get 4. We get x to the 5/6. And if they had asked, we would see the 6th root of x to the 5th as the answer. You could go back as well. They are of equal value. All right, many of us have not seen this next one, this double radical symbol. It is totally legitimate. We have seen it in an alternative form. I guarantee you, you have seen this at some other version of it. You maybe not have seen a double radical, though, because let's be honest, it looks ugly. So how can we fix this? We can first take that under radical to a 4th, and the top radical is a 1/2. And now I simply multiply the fractions. And multiplying fractions is so convenient because I just have to do the tops and the bottoms. In other words, this is z to the 1/8. And that's why you don't usually see radicals being compounded on top of each other, because they usually just combine them anyway into an 1/8 root of z. But again, of equal format. All right, let's keep going here. I see some y's. I might be able to combine them, but first let me reorganize. Oops. We've got yz to the 1/3. Now you might be thinking, well, shoot, that y is stuck inside that 1/3 there. How can I combine it with the other one if it's stuck, right? Well, I just need to give each one of these. There's no addition in here, no subtraction in here, and so it is a lot more maneuverable. Remember, multiplication, division, and exponents, they like to play with each other. It's addition and subtraction, they're usually picky. And so I can combine these first two. 1/2 would be 3 6s. 1/3 would be 2 6s. Z we can keep as a third. And so we have a total of 5/6 on the y and 1/3 on the z as my final answer. All right, luckily these last three are not written as radicals, but they are still a hot mess. I see lots of different things that we could do here, and so let's clean these up a little bit. I can distribute this 4. 4/2 becomes 2. And y would get 8/3 if I multiply 4 and 2 over y to the 1st. I can go ahead and subtract those y's. I've got 8/3 on this y minus 1, aka 3/3, which gives that top y being 5/3 as my final answer. All right, this next one has the entire thing being being raised to this negative fractional power. We've seen a lot with this negative fractional power today. I'm actually going to deal with the inside first, mostly because I don't want to have to deal with all those fractions, and there's a lot less fractions inside. So let's just save that negative 2/3 for the end. If I were to take the negative 2 on the bottom here and move it to the top, I get x to the 2nd, x to the 4th. Same thing here, move it to the bottom. Y to the 6th, y to the 1/3. Because that's what the negative exponent says. It says flip the side, right? And so now I'm here, I see some stuff I could combine here, x to the 6th. Here, careful, that would not be 6/3. 6 is 18/3, and so this would be 19/3. And now it's still being raised to the negative 2/3. Much easier to deal with. Multiply that, you get x to the negative 12/3, aka negative 4. And then y to the negative 38/9, not as pretty. Both of these negatives will cause the fraction to flip completely over, but not change their values. And I'm done. I know I'm finished because I have one of each type of base. There's no more double y's, double x's. Everything is positive exponent-wise, and there's no more parentheses. That's the 3 indicators that you are finished. This last one is the worst case scenario. It has a lot of the rules in there. It is meant to test you, so I strongly recommend you pause the video, try it on your own, see how it goes, and then come back here and see if you got it right. All right, hopefully you had a chance to pause the video. Here we go. Again, I think, well, see how this parenthesis is not around the entirety of the thing, and there's nothing to actually do in the parentheses. So I think I'm going to go ahead and take care of that one. So I just copy pasted the top, but on the bottom here we have a positive 8/5 now due to that negative canceling out, but for the x we have a negative 2/5. Okay, I see a lot here. I'm going to go ahead and add the tops. In fact, I might do, if you're up to it, you could do all at the same time. You could do adding these two and subtracting that one all at the same time, but I think I'm going to go one step at a time. So let's go ahead and leave that bottom one there and that one there. Yeah, and so y to the 2/9 plus 1/3 would be the same thing as y to the 2/9 plus 3/9, which is y to the 5/9. Goes back up top. Alrighty. Next up we have x to the 3/5 plus 3/8. Unfortunately, 3 and 8, or 5 and 8 don't have a lot in common. I'm thinking 40 is actually their first thing, which means I'm going to have to multiply by 8 on this side, 24, and 5 on that side, 15. We add those together, 39. Ooh, so close to 1. Bummer. So we get x to the 39 out of 40. From there, I think we can pull that up there, and so we get y to the 5/9. You might want to be careful about how you write that. X to the 39/40, x to the 2/5 out of y to the 8/5. Okay, I think I'm going to subtract these two. So y to the 5/9 minus 8/5. Remember, one of the best things about a video is you can pause and rewind. So if you got lost, you can go back and figure out where you got lost and keep going through. I'm going to change these to 45, which means I multiply by 5 over here and 9 over there, which gives me y to the negative 47 over 45, which means it's actually going to hit the bottom. So I have over y to the 47 over 45. Now, if I were to add the x's here, I got x to the 39 over 40 plus 2 over 5, which is 39 over 40 times by 8 to the second one. You also get 40, so plus 16. We get 55 over 40. And so on the top, we have x to the 55 over 40 as our final answer. Once again, it doesn't look very pretty. There's a lot of half pieces going on here. We have so many radicals within radicals within radicals hidden in this problem that it's not going to ever end up looking beautiful. But it's got one of each base, it's got no negative exponents, and it has no parentheses. We are finished. Alrighty, that's the end of the rational exponents videos. I will see you again for complex numbers in 8.5. See you there.